Hi. Hello, everyone. Super excited to be here. I'm Pratibha Suryadevara, VP of Engineering at Google Cloud. The next 45 minutes, we're going to dive into the world of graphs. We're going to talk a little bit about how Spanner is uniquely positioned to run your graph workloads. We'll talk about the latest capabilities that we are working on. We cannot not mention GenAI within the first 1 minute of the session. Yes, we'll talk about GraphRag. We'll talk about GenAI capabilities. And another exciting capability, the hybrid search techniques that we can use to get the tailored contextual responses for your GenAI applications. So it's going to be an exciting thing. So joining me with me today is Bailey, engineering manager, founder of our Spanner Graph. Delighted to have Spoorthi Ravi, engineering manager at Snap. Okay. Like the next 45 minutes, we'll do just recap of what graphs are. We'll talk about how we've reimagined Spanner Graph, what we have done to make it the most reliable, most scalable, most suitable environment to run your graph workloads. Then we'll have Spoorthi walk us through how they're using Spanner Graph to run their identity workloads, which has billions of users at Snap. We have an exciting live demo from Bay. And then we'll talk about a little bit of capabilities that are coming up, and hopefully we'll have time for Q&A. If we run out of time for Q&A, we are always there outside. We'll spend some time answering your questions. Let's dive in. Let's just spend a minute or two on what graphs are, right? So graphs are basically data models optimized for relationships. We think of graphs as just nonlinear data structures containing nodes and edges. Like for us, when we're building these, it's pretty much nodes are the entities and edges are the relationships between the two. This is a just simple example of one of the graphs. In this graph, we have like people, the skills they have, the places they live in, and we can build applications like recommendations around what member groups they want to be and stuff. I think graphs are everywhere. If you look around, whether these are retail graphs that we have, where they think of relationships between who's buying what products, what recommendations we want to give them, or the transactional ones around financial systems, right? Who is doing what transactions from what country, what locations, are these fraudulent transactions? How do we want to think about these? So we think the use cases for graphs are like endless and infinite, right? Across multiple verticals, right? Whether it be retail, financial, telco, supply chain, drug discovery, network security, I think the use cases are pretty infinite. So then the question is, hey, I understand graphs. I understand it's used for representing relationships. Why can't I use existing data structures to represent it, right? You have all the relational models today. Yes, we can. You can use foreign keys. You can use joins to represent that. But very quickly, it becomes very, very complicated, right? I have a very simple example where you have maybe trying to build an application where it's a friends of friends, and you're trying to figure out what posts these people have liked. People are across different countries. These are friends and friends. If you're trying to build a SQL for this, right? If you represented this in a simple relational table and built a simple SQL query, it becomes very complicated very quickly. Compare that with what you can do with GQL. It's a simple few lines of code that you can write to understand the relationships between these. So I think so far we discussed what graphs are, what we want to use these graphs for, and we think that graphs are the right way to model these relationships. And these graph databases, because of their query specialization, because of the graph languages they support, and also at times the memory structures that are set up, are the ideal tools for running graph systems or building applications where you want to understand deeper relationships between. We talked about graphs are amazing. We talked about they're applicable everywhere. But we all know graphs don't have the adoption, right? Then if it's so amazing, why don't we see graph adoption the same way we see the adoption that we have for other relational NoSQL or document stores? About 2 years ago or a year and a half ago when we started building Spanograph, we talked to hundreds of customers understanding why don't we see this adoption? What are the challenges for you? It kind of summarized into 3 set of challenges, right? It started with operational overhead. We all know, I think, graphs are not the single source of truth. They're usually backed by another relational store. What it means is you're building pipelines to duplicate that data. You're managing those pipelines. You need to worry about the security compliance of this. Yes, we put all this effort. We are ingesting into a relational store. We have built the pipelines. We've scaled. We put everything together. End of it, you would be disappointed with the SLA that you're getting if the SLA of a graph database is lower than that of your relational database. The second one is the scalability limits, right? We all know these graph queries are very compute intense, and the compute needs are not very predictable because generally they span out. A simple example, if I have a 2-hop query, and I'm looking at the performance of a query, if the node is a celebrity versus a regular person, the performance is going to be very different. The way some of the systems tried to solve this problem is, hey, why don't I actually scale the writes vertically, and I'll scale the reads horizontally? But we all know vertical systems have a finite scale. So what that means is you can't build large graphs. So that has been one of the challenges that most of our customers highlighted. The last one is a learning curve. Yes, we said graph languages are amazing, easier to program in. But before we had standards, SQL was available for graphs only later part of 2023. What we did with label property graphs was not a standard till only after we have GQL is where we are actually getting to the standards. So with this with this mind of these are all the challenges that we have, I'll invite Bay to walk through the approaches that we took to build Spanograph to solve some of these challenges.
OK, all right. So this is Bailey here. I'll be leading the Spanograph effort since the beginning. So like Pratibha mentioned, right? So since very early days, we try to understand why you are using graphs in the first place, what kind of value it brings to you. But even more importantly, we want to understand why you are not using graphs. What kind of frictions are there? Right? So essentially, we want to keep the good things and remove the bad things for you. So in addition, we actually looked into Google internal systems and learned lessons from there as well. So if you remember, Google actually has a very long history with graphs. So even 25 years ago, our company founders invented the PageRank algorithm. PageRank algorithm is actually a graph algorithm. Right? It projects the whole web into a citation graph. And then essentially nodes are web pages, and edges are hyperlinks between the web pages. Then you propagate the scores through these links. And when you converge, you get the centrality scores, which are essentially how important this web page is in your entire web graph. Right? So, and then this centrality score is used in the ranking. Right? So you all know how well it works. Right? Google becomes very popular. Another example is actually knowledge graph. So more than a decade ago, so Google introduced the knowledge graph. So knowledge graph is essentially the knowledge of the whole world, right? So it has places, things, and people. So essentially, when you search in Google.com, you will type in search queries. We actually translate the natural language you type in into graph query, into many graph queries actually, to fetch the data from this knowledge graph. Then we produce the answer for you. Right? So essentially, knowledge graph turned Google.com from a search engine only to an answer engine. Right, so I personally actually spent 6 years writing code building knowledge graphs, and I had a lot of fun there. So essentially, we took the lesson learned from you. Again, thanks a lot for the feedbacks. Right? And we took a lesson learned from the Google internal systems. We folded them into Spanograph. So this is actually decades in the making, in a sense. OK, so what is Spanograph then? So it has 3 main pillars. So the first pillar is the native graphic experience with SQL interoperability. So the second pillar is the search on graphs. And then the third pillar is the scalability and the performance. So let's actually dive right in. So first of all, spanner graph is a graph database. So we want to make sure that the experience is smooth. For that, we provide you native graph experience with GQL. So GQL stands for Graph Query Language. It's a new ISO standards, released, I think, April last year. So Google and many other graph vendors actually got together for past 6 or 7 years, actually. So, working on these standards. Eventually, luckily we published it. So Google actually one of the early adopters of GQL. So if you look at the GQL syntax, you probably don't feel it's very foreign. So if you are familiar with a query language called OpenCipher, it's mostly evolved from OpenCipher. So there are a few differences. For example, in the first line, you need to specify a graph to query. That's because Spanner actually supports creating multiple graphs within a database. So you have to specify which graph you want to query. And the rest, you can see there's a match statement. So that's a core part of GQL. It's a graph pattern matching. Right, so you can see the syntax. I hope even if you haven't learned any graph before, I hope it's easy to understand. Essentially, you use parentheses to denote nodes, the arrows to describe edges, right? So essentially, you traverse from a customer named John, traverse its no edge, 1 to 3 hops to reach a target customer, right? I hope it's very easy to understand. And then the rest of query is mostly similar to relational queries, right? It's order by, limit, and return. But how are these queries executed? So we all know graph queries are very performance sensitive. So for that reason, we actually optimize these operators quite a bit. For example, like match, optional match, quantifications, path modes like any, trail, and walk, and path finding algorithm like shortest path and cheapest path. Right, so we adopt multiple optimizations, for example, vectorized processing, factorized processing, to essentially process your edges in bulk or process them in a very compressed form. Right, so there's actually a lot of optimization went into this. I will give you a quick example. For this query, remind you any, if you see any right beside the match, the second line. So the semantics of any is actually a reachability. Right, so let's say if you have 2 pairs of nodes, so you want to just keep one path. Instead of all possible paths become this one pair of nodes, you just keep one, right? You want to dedupe. So when you run this query, there are 3 main operators to support this query. There's the scan, starting nodes. You want to find, the first node is John, right? You want to find that node. And then, you find that node through that operator. Then the recursion operator keeps track of the node you already visited. You want to make sure you don't do duplicate computation. Then you expand from J to A and B, 2 more nodes it connects to. And again, the recursion keeps track of the A and B, right? You want to dedupe along the way. Then, you keep expanding from A and B. They reach a common node C. But if you recall, the semantics of any is to keep one path between a pair of nodes. So now between J and C, if you don't remove the one from B to C, you will have duplicated path. So we remove that one. The moment we find out the duplication, we remove it. So you don't waste your computation and then come back and remove. We do eager pruning versus late pruning. Then you traverse again, right? So from C, you reach A and B. And because A has been already visited before, right, we also trim that path. Right? And then you have essentially the result. So you can see as we go, we remove all these duplications, right? So that's one optimization among many other optimizations we had. And for the rest of the query, you can see order by, limit, and return, they are not really graph specific, right? So in SQL, you saw the similar things. So for that reason, we didn't try to reinvent the wheels, right? Because what's the value of doing that? We want to focus on the graph problems. We don't want to reinvent the wheels for no values. So we reuse all these relational operators. So besides the operators, we actually reuse the data types, functions, and expressions too. Because, for example, string in a graph is a string in SQL. What's the difference in these data types? So we didn't find any value of reinventing all this. And because of this deep fusion of this relational technology and graph technology, we can do a lot more powerful things. For example, here's one example. You have full interoperability between SQL and GCode. This rectangle, if you can see, that's the same graph query we showed you before. But because of this deep fusion of the technology stack, you can essentially embed your SQL and GCode together, right? So you can use the graph to do what graph is good at, like traversing relationships, but you can use the rest for use the SQL, right, if you are more familiar with it. So imagine you have a group of data scientists who are really familiar with SQL, and you want to introduce graph to them. Like, how do you do it? Right? So instead of asking them to, okay, so now you have to do GCode for everything, you can just tell them, you can just keep using your SQL. But only for the parts you feel it's very hard to do in SQL, you can embed this little GCode there, right? You don't have to do everything all at once. So you can gradually, expand your GCode knowledge and do more and more GCode, right? So this is essentially making sure the learning curve is as shallow as possible. And search on graph is also very key, right? So sometimes, because graph is, is for relationships, right? Traversing relationships. If you want to find a rich information about something, let's say like shoes or something, and you can not only look at the shoes itself, you can traverse its relationship to find more like producers, buyers, or brands. You can just traverse a few steps deep to find the richer information. But how do you get started? Like, how do you find the starting nodes, right? You have to find the starting nodes to traverse the graph. So search is actually for that purpose. So let's say if you want to find more information about hiking shoes, and you can essentially just use search to find the starting points, and then you traverse the graph, right? So this is actually very common, especially now the Gen AI age, right? So you have natural language as an input, and you want to ground your foundation models with a knowledge base. This is actually the thing. Like, this is the glue between this foundation model and your knowledge base. So how are graphs created in the first place? Right, so we have this, the opposition is there's already a lot of connected data, but they're stored in the tabular format. So if you remember the entity relationship modeling you learned on the graph school, it's about modeling graph in tables, right? Entity and the relationships, they're essentially nodes and edges. But right now, we want to give you the reverse mapping to essentially produce the graph from the tabular data you already have. So here's one example. You have tables, and then you use the schema to reverse them back to the graphs on the right-hand side. There's a lot of benefit. There's no ETL, no data duplication, no data lag. Data governance is no longer a problem. Okay, so I will just quickly go through how data is stored, because the format is important, right? So in spanner graph, we actually store the nodes and edges together, so that when you do traversal, it's a simple I/O, right? So you don't have to issue multiple reads, and from the disk or from the storage or from the buffer pool, we just minimize the number of pages you have to read. And all these are stored in actually clusters, which is our cloud storage. So the disaggregation of the compute and storage is very key, right? For example, you can access the storage without really going through the spanner servers. You can essentially decouple this. Isolation is really good in that sense. In summary, we have a native graph experience. We have interoperability between GCode and SQL. And we have search on graphs. We have a virtually unlimited scale. And we have a competitive performance. And it's on top of Spanner. Just very quickly, why we choose the Spanner as a foundation. So many years ago, when we started this effort, we looked into the technical stack of a graph database. So there are many parts of that database is actually graph-specific, but there are so many parts which are not really graph-specific. For example, transaction management, right? You want to commit your data atomically. So it's not really graph-specific. Like data import, export, load balancing, so monitoring, alerting, resource provisioning, and the control plan. All these are not really graph specific. So we want to save our energy to focus on the graph thing. And Spanner, on the other hand, is very used widely in Google, right? All the payment, search, ads, they all use spanner. So it's unlimited scale, very high availability. So there's so many benefits we just built on top of this platform. All right, so so much about spanner graph. It might sound good on paper, looks good on paper, but how does it work in reality? For that, I would like to invite Spoorthi on the stage to give us the insight of how Snapchat uses spanner graph.
Thanks, Phil.
Thank you.
Hey, everybody. I'm here to talk about a few graph use cases at Snapchat. Snapchat itself can be thought of a large graph where the users, their friends, their content, ads can be modeled as nodes, and the relationship between them can be modeled as edges. Our communication graph has over 1 billion user nodes and 10 billion communication edges between them. Today, in particular, I want to cover the Snap Ads attribution use case, which involves identity matching. So what is identity matching? It involves the process of identifying users and matching them with events that happen both on Snapchat and off Snapchat. We utilize various signals to identify these users, such as cookies, hashed emails, IDFEs, etc. Why is this so important for Snap? This directly improves our direct response ads because we can then attribute a conversion to Snapchat. This also increases the availability of third-party signals so that our ad ranking, targeting, measurement models can get better. So let's go a little into what the current system looks like and what are some of the issues with it. The current identity matching system is built on top of KV stores, which works well up to 2 hops. Here, for example, if we get a conversion event, you can see a bunch of KV stores here, and we try to match that event. If there's a match, great. If there isn't, we do some offline processing to get a probabilistic match. At the end, we can only go 2 hops. We need to be able to go multiple hops at scale to better improve our match rate. Additionally, another issue is staleness of data. So if there is a linkage that comes through that we can't immediately match, let's say like hashed email and a cookie, and there's no direct match on these tables, we aren't able to augment this graph immediately. We need to do offline processing. It takes a while, and then we're able to augment this graph. So how can graphs help? Graphs have the ability to add real-time connections to the graph, both edges as well as nodes, ability to traverse the node more than 2 hops at scale. Also, we're able to compute graph analytics on top of it, multiple algorithms like PageRank, that we can then augment the graph with node and edge features. So by modeling the identity data as a graph where the personal identifiers I mentioned, like hashed email, cookies as nodes, and the relationship between them as edges, we're able to traverse the graph more than 2 hops at scale. We're also able to give our ML engineers the ability to run different query models to improve our match rate. So a little bit about the size of the identity graph at Snap. So we have over 20 billion user nodes. So these are the personal identifiers I talked about, like hashed email, cookies, IDFEs. Edges, these are the relationships between them. And these come from both real-time events as well as linkages that we get after offline processing. We have over 10 node and edge properties, and the total size of the graph goes over 10 terabytes. So let's take this example to kind of understand a little bit more of how a graph is better than a KV store for identity matching. So looking at this, let's say the current graph has like 3 linkages, a user ID to cookie 1 to cookie 2, and cookie 2 to a hashed email. And we get a new event which contains 2 PIIs, which is a hashed email and a completely different cookie, cookie X, saying, this email and this cookie bought X, right? So given the existing linkages in the graph, we are able to match cookie X with user ID, as you can see. The graph query would look like this. Retrieve the first matching user ID starting from cookie X, or this node, with a max path length of 3 to 4. So why spanner graph? So a concern with graph DBs have been availability, scalability, and especially for a system like ads attribution, where we do need the identity data to be persistent, we need a system that's fault tolerant, highly available, and can scale. So Spanner offers sub 100 millisecond latencies for 3 to 4 hop queries. It also allows us to scale horizontally with social workloads not being predictable. During NYE, Black Friday, we have a lot more events than normal days. And we need to be able to immediately scale without having any downtime. Additionally, it's available, it's managed, secure, and also we have endpoint recovery. So we built the identity graph on Spanner, and we see some really great results. With really low latencies, 3 to 4 hop queries, where P99 is over around 50 milliseconds. It can horizontally scale with traffic increases. We're able to add new events and linkages in real time. We're also able to capture relationships that we couldn't before because they needed so much more offline processing. In the future, we would want to run like graph analytics and graph algorithms on subgraphs so that we can further enhance the node and edge properties. With this, I will hand it back to Bay for a demo.
Thank you, Spoorthi, for the great insight of the recommendation of the identity resolution in Snapchat. So that is one of the key use cases of graphs, right? But that's not the only one. So let's say we have a recommendation, we have a fraud detections, we have a root cause analysis, and many more, impact analysis, for example. So here I will just show you one example of a recommendation, right, using spanner graph. So let's say you are an engineer. So can we switch to the demo? OK. So let's say you are an engineer working on a retail website, and you want to build a recommendation engine. Right? So the experience is going to be when a user comes to a website, if they do a search, so not only you want to return the product they are searching for, you want to return other things that are relevant and they might be interested in. Right? So you want to like cross-sell and upsell. So let's say to begin with, you want to start simple. Let's say you just want to return things they are searching for. Like remind you, Spanner supports search, right? So in this quick example, you can see I'm select star from product table and using this search function to return like waterproof hiking shoes. So if I run this query, you can see, well, this is a simple demo. You can see there are multiple products returned. They are essentially all some kind of hiking shoes. So this is a great start. But you don't want to stop here because you have so many other things people or your user might be interested in. Right? So, and you want to try luck with graph. So because graph is about relationships. By finding all these connections in your retail graph, you might be able to find more things people are interested in. So let's say you want to try the graph. And again, you want to start simple, right? You don't want to go like too far each step. So you can do the same thing with search, right? On graph, it's essentially the same search function, and just like in the GQL syntax. If you run this simple query, you can see you have these 3 products returned, right? So they are all, again, the same 3 products. It's a waterproof hiking shoes related product. And then these are like rendered as nodes in a graph. And now you want to go a step further. You want to follow the relationships and to find the things commonly bought together with this, waterproof hiking shoes. For that, you use graph. So in this graph query, I hope it's very easy to understand. Right? So you still do the same search to find the product, which are waterproof hiking shoes or boots. You traverse its purchase edge to find which customer bought it before. Then from there, you traverse the purchase edge again, but in the forward direction, to find the things they bought, right? The users who bought these waterproof hiking shoes, what else did they buy? So you can see this is a simple relationship traversal using GQL. If you run this query, you can see there are many, many things got returned. So before you only had the 3 products got returned, which are like essentially what you searched for. But by following the relationships, you can see there are like 20 products returned, right? So if you can see them, they are hiking shoes for sure. They are like hiking poles, hiking socks, right? So backpacks, headlamps. So they are essentially the essentials for you to have a nice, enjoyable hiking trip. And you are a good, solid developer, right? You don't want to stop here. And you remembered, so there are tables which record the past price points of this product. You want to surface this to a customer or users to make sure they have an informed decision if it's the right time to buy. But because the information of the price history is actually in tables, like you are using graph and there's a table, like what do you do? But with span graph, you don't have to do complicated things. If you remember, in span graph, we can actually combine SQL and GQL together. Let's switch to this query. It's essentially the same query, right? So these parts, these graph parts, you can still remember, right? So there's match, and there's a product, and there's a search. But that's exactly the same graph part for recommendations. But after the graph search returned all the recommended product, you can do a drawing of the price history table, right? And essentially, you bring graph and the relational and graph together. So if I run this query right now, you can see, so all these products are recommended before, but now they are enhanced with the price points, right? So, and now you can surface this to a customer to have so they have a more informed decision. This is a very simple demo, so I hope you like it. So if we switch back to the slides. All right, okay. So since our public preview last August, right, so many of you showed interest of spanner graph, right? So of course, many of you launched on spanner graph already, right? So there's a lot of good feedback. So essentially, you say you want more, right? You like what we offer right now, but you want more. So, and we've been working closely with so many of you to see what's the right thing to build, what's the priority, right? So Graph Rack is one of the things, right? So there's so many requests about Graph Rack. Essentially, you see the limitations of Rack because Rack is based on the text trunks, right? So it doesn't have all the rich information in the trunks, right? You have to use vector search to find the relevant trunks, but you cannot follow the relationships. So for that reason, we launched spanner graph integration with LangChain. Right now, you can use LangChain to essentially turn a text document into a graph backed by spanner graph. You can actually ask natural language questions using LangChain. Right? We have some fine tuning or prompt tuning to make sure the translation is correct. Right? So many of you actually are already using it. So visualization is a key experience. Right? So because graph, again, it's for intuition, right? It's very intuitive, easy to communicate if you visualize them as graphs. For that reason, we launched the Studio experience, which you just saw, and we also have a notebook, right? So it's open source. And also, we heard from many of you that you have a lot of data in BigQuery, and you want to serve it at a low latency. So we have a reverse ETL from BigQuery. With one simple command, you can essentially bring your data to spanner graph for fast serving. Performance optimization is never-ending journey, right? Because again, graph is about relationships. So you want to traverse deeper and deeper, right, to find more and more things. So we are always tuning our performance. Emulator, right? So you want to test your things before release. A graph now is supported in Spanner emulator. So the last item, we're going to enter the preview very soon. So especially in the Gen AI use cases, many of you said you don't necessarily know the schema beforehand. You want to handle this open data. So we are now adding the open data modeling support into Spanner Graph, again, which will be previewed very soon. And furthermore, so graph visualization is such a critical piece of the graph journey. So we've been working with many partners closely. Linkuris, Graph History, Canvas, and G.V, they are already supporting Spanner Graph. So actually, many of them are actually here, right? So if you are interested, please talk to them, right? So I love the product they built. Okay, so here's one more thing. So again, since the very early days, we try to understand what you really want, right? What kind of problem you have at hand. So we heard very early on that you have operational workload. So in fact, you have very diverse workload, right? Besides operational workload, you also have analytical workloads. So in the very early days of building spanner graph, we keep that in mind, right? So we wrote code in a way that is mostly reusable, right? And lately, we've been working with our BigQuery partner to bring the BigQuery graph to the picture, right? So the spanner graph, you can see that's the one stop of the journey, of the graph journey on Google Cloud, but that's not the last stop, right? So the journey continues. So they support the full spectrum of operational and analytical workloads. They have a unified graph schema and query experience. Visualization is also a key part. It's almost the same. So there's a very smooth data flow between these two systems, query federation, graph fabric, and ETL, reverse ETL. We want to make sure this is really a unified solution for you, right? So on Google Cloud. Okay, so spanner graph is already GA, right? So many of you are already using in production. So you can scan the QR code here to get started. There are like user guide, collabs, like more examples, blog posts. You can find more about spanner graph. And there are two more sessions, but Equifax is getting on the stage to share their experience with graph. And there are more sessions, right? And your feedback is always welcome. So besides the product feedback, feedback about this talk, right? What do you want to hear? So there's just so much to talk about, right? The same deck, I can talk to you more, like 2 more hours. There's no problem. There is so much to talk about. Let us know what you want to know. We will definitely do that next time. Okay, thank you. So right now it's QA time. I hope you like this.
Any questions we can? I think there's a mic going around.
So can you talk more about this reverse ETL from BigQuery?
Yeah.
Go ahead.
Thank you.
Go ahead.
Okay. So essentially, reverse ETL tells you. So essentially, it's just one command, right? So you specify which tables you want to port from BigQuery to Spanner. You specify the essentially destination, the instances, and the tables you want to migrate data to. Right? So that's one command you can essentially behind the scene the data will be like continuously be streamed into Spanner.
Yeah, I think the way we look at Spanner and BigQuery is as a single data systems. So when we talk to our customers, they talk about ingestion use cases where they're ingesting data into BigQuery, but they have some low latency real-time analytics they would want to run on Spanner. So we've created a seamless mechanism where you can actually stream that data back into Spanner and serve that data from Spanner. So you can use that for graph, you can use that for native analytics, you can use for any of those kind of use cases. So the idea is single system, you can figure out where you want to serve that data from. Yeah.
I have a question here.
So for like a typical RAG use case, you have all this, like say company documentation, and you have this doc and you need to parse out relationships. I don't fully understand how you parse those relationships. Is that something that's manually defined, or?
Yeah. Okay. Good question. So essentially, there are different approaches. And so we find the approach where you roughly specify what type of relationships or what type of nodes you are interested in, almost like a soft schema. So that is more efficient, right? Because LLM, they can read the document, they don't necessarily know where to focus. Right, so if you just give them a hint, okay, this is the set of nodes and edges that I'm interested in, the quality and recall we observe is better. So based on that, we will, like with LangChain, for example, we will create a spanner graph schema and import the documents, the relationships extracted and into spanner graph and for query.
I think there was a question here somewhere. Yeah.
Kind of a noob question here, but oh, sorry. Kind of a noob question, but do you guys, how does a spanner graph handle hot nodes?
That's a good question. So essentially, there are multiple technologies. Right? So first of all, hot nodes are the ones with a lot of fan in, a lot of fan out. Right? It happens a lot in the natural graphs. Right? So essentially, we have a optimization. I kind of mentioned on stage. One is vectorized processing. Right? So for the hot nodes, we don't process, even for the regular nodes, in fact, we don't process these outgoing edges or incoming edges one by one. We do them in bulk. Right? So it's essentially like a scan almost like hundreds or thousands of them at the same batch, and we process them. So another thing is called factorized processing. Because hot nodes, let's say if you have a very high fan in, high fan out hot nodes, when you traverse across it, your data becomes, intermediate data becomes very large. Right? So it's almost like exponential in a way, Cartesian product. Right? So we are introducing something called factorized processing. So when you go through these hot nodes, we make sure we compress the intermediate results, so you don't kind of exponentially explode the results. So also we are building something called sampling. So very often you don't always need all the information about these hub nodes, right? Because like what you do with like 10,000, like 1 million edges. So like say you are doing machine learning or something, very often sampling is good enough. Right, so we actually have a built-in sampling operators as well, so like tailored for machine learning use cases. But there's like, because there's so many about this topic already, you can always mark your hot nodes. Like if you don't really care about this so many edges, you can trim them. Yeah, that's the thing we have right now.
I have a question.
Yeah.
Thanks. This is awesome. This is really exciting. Obviously, talking about graphs, we immediately start thinking about Neo4j. And they've got a couple of analytics out of the box, things like PageRank and community detection and those kind of things. Yes. So is that on the roadmap?
Yes.
And when is that coming? And then additionally, in the same sense as well, shown the full text search. Yes. When do we get multimodal search, like image search, as part of it?
I can answer the search one. And I think, yes, ML algorithms are the next thing. We didn't want to put it on this thing because it's like we were told not to put roadmap things here. So we can follow with you online and offline and tell you what this is. I think one of the things in Spanner that we are super excited about is this multimodality that you can bring between full text search, semantic search, and vector search. The Spanner full text search is actually built on top of the same advanced search queries that we do for Gmail and our Google search and Docs. So the use case that, the demo that Bay has shown was actually token-based search that you're merging along with graph to find the node in the graph. So full text search on graph on Spanner is already GA'd. Semantic search both for vertex integration, ANN and KNN is also GA'd. So now you can build these very exciting AI applications that are hybrid search first, then you find the node in the graph that you want to start with and traverse. So it's opening up really very exciting and different use cases for us.
Yeah, a quick question. Yesterday in the BQ graph session, Candice mentioned a query where we can merge both Spanner and BQ, like an external source.
Yes.
So is that the other way around as well? Using external source as BQ and trying to merge, federated query? You want to take that?
Yes. So essentially, the thing you mentioned, it's I can give you a little bit more context. So we realize there are a lot of use cases where you don't necessarily have all your data stored in one place, but let's say due to governance issue or ownership issue, but we want to build a virtual knowledge graph across many data sources, right? So for that reason, we are actually supporting something we call Graph Fabric, right? So essentially, again, like building a virtual knowledge graph spanning multiple data sources. So BigQuery already, like yesterday, you saw the slides, right? You can essentially create a graph using multiple tables, some are stored in Spanner, some of them are in BigQuery. So you can create a graph out of it. So these tables can be backed by different data formats, or like Iceberg, or some Parquet files or something, or stored in Spanner natively. You can do that.
Yeah.
And we have more.
Yeah, thanks everyone. We are at time, but we'll be outside there in the hallway. We can take more questions. I think we are at time. We'll meet you all outside. Thank you.
Okay, thank you.